Hello again. We'll look at one more problem in mathematical induction that involves inequality. What I have here is I'm just going to arrange my windows here. So let's get this on the right. Okay. So the problem is prove the following, where I have 2 to the power n is less than n factorial for every positive integer n, such that n is a positive integer that must be greater than or equal to 4. Okay, so what is the proposition here? The proposition here is basically restating the problem, which is I'm going to state it in terms of p of n, where p of n is the statement that 2 to the power n is less than n factorial for n being greater or equal to 4. Okay, so what is the basis then? But basis over here happens to be where my n, the first element in this universe of n, happens to be 4. Okay, that's the very first item. And so in this case, if I plug in where n equals to 4, I get p of 4 here, where p of 4 is basically this is going to be 2 to the power 4 is less than 4 factorial. And let's just show this whether this is actually true or not. Well, 2 to the power 4 is 16, and 4 factorial is 24. So I can show this is easily seen that the basis step is also true. Okay, now I don't know what's happening to my handwriting today. It's getting really, really terrible. But let me maybe put it this way. Okay, that's the basis. Okay, so what's the inductive step then? Well, the inductive step is basically the idea that I must show for all k, if p of k, then p of k plus 1. Okay, and what this tells you is that this orange box must be true. Whatever's inside this orange box, which is conditional statement, must be true for all k. Okay, and because it needs to be true for all k, okay, let's assume that if I choose any arbitrary k, okay, I'm going to choose some arbitrary k out there such that this k happens to be greater or equal to 4, but it's some completely arbitrary k, and for that arbitrary k, I'm going to assume that p of k is true. If p of k is true, and this orange box must be true for all k, then I must be able to show you that p of k plus 1 must also be true. Let's see. Let's use mathematical induction to see whether p of k plus 1 is also true. Now, how do I do that? So let's rewrite p of k again. So this is good. This is 2 to the power k less than n factorial, and we're going to assume that this box is true. And again, let's not use n. I need to use k there. So this is k factorial. So we're going to assume that everything in this box is actually true for some arbitrary k out there. Okay. Now, if it's true for this k, can I show you whether p of k plus 1 is actually true as well, which is 2 to the power of k plus 1 is greater than k factorial. Okay, I don't know this right now, but we're going to use mathematical induction to prove that this is also true if p of k is true. Okay, so let me use a slightly different color here. Let's use maybe let's use blue. Okay, so 2 to the power of k plus 1, as per the definition, we know that this is equal to 2 times 2 to the power k. Okay, it's just the basic middle school definition of exponents here. Okay, so 2 to the power k plus 1 is equal to 2 times 2 to the power k. Okay, now let's think about this. If I have a number like such as 7 over here, I'm writing 7 as 7 times 1. Okay, I can always take the equality. I have an equality here. I can take the equality out and replace that with an inequality, something like in this case 7 is less than. Okay, 7 is less than. As long as I plug in something over here in place of either 7 or a 1, a number that is greater. Meaning that if I replace 7 with a number that is greater than 7, something like, let's say, 100. Okay, this definitely is a number that will be greater, and because it's greater, this equality has been changed into this inequality sign. Okay, so 7 in this case has been replaced with a number that is greater than 7, which happens to be 100. If I apply the same logic over here, such that if I take 2 to the power k plus 1, I have an equality here. I want to replace the equality with the inequality, meaning in this case I'm going to use the less than sign. So I need to either replace 2, or I need to replace 2 to the power k with some number that happens to be greater than either of the two. So let's keep 2 as it is. But in place of 2 to the power k, I'm going to replace this everything in the box with some number that is greater than it. Well, I already know, I'm assuming that P of k is true, and because P of k is true, this number is right here, k factorial. I know that k factorial coming from this box is greater than 2 to the power k. So I'm going to write over here k factorial. Okay, so what I have so far is I'm trying to come to this I'm trying to show you that P of k plus 1 is true, meaning 2 to the power of k plus 1 is less than k factorial. Well, what I have here so far in blue is 2 to the power of k plus 1 is less than 2 times k factorial. Okay, so I'm somehow getting closer and closer to this pink statement, but I'm not there yet. So what I'm going to do now is, I'm going to take this, I already have a k factorial here, and there's already a k factorial over there. Okay, and again, there's a slight typo here. This statement in pink, it should not be k factorial. This should be k plus 1 factorial. So let's correct that. Let's make this k plus 1 factorial. Okay, so everything in blue over here, I've got 2 to the power k plus 1 is less than 2 times k factorial, which means what I can do now is, let's take this number 2. Let's take this number 2 and replace that with some other number that happens to be greater than 2, so that the inequality is preserved. I don't want my inequality of less than flipping over to something where this gets flipped over to saying greater than. I want to preserve this inequality. And the only way to preserve this inequality is as if I replace the number 2 with some number greater than 2. Okay, so what if I do this? If I do 2 to the power k plus 1, and let's replace 2 with, let's say, 20,000. Well, 20,000 is definitely greater than 2, so I can put that 20,000 in, no problem, times k factorial. Okay, this is fine, this is good, but it isn't really helping me. Sure, I have preserved the inequality. I've replaced 2 with a number that is greater than 2, so this entire expression inequality is also preserved, but this isn't helping me. It isn't helping me to move from the step to the step that I would like to eventually get at, which is this entire expression in pink here. So let's think about this. I still want to replace 2 with a number greater than 2, but instead of putting in something like 20,000 there, let's put something that will allow me to approach this pink statement. So what I do know is that this number 2 and k plus 1, I do know that k plus 1 is a number that is greater than 2. How do I know that? Well, I know that this inequality of n being greater or equal to 4 is going to be we are looking at only those n's that happen to be greater or equal to 4. So if I plug in 4 here, this makes it 2 is greater, or in this case 2 is less than 4 plus 1, that makes it 5, where this is nothing but 4 plus 1, where I made k equals to 4. And likewise, if I choose any value of k, where k happens to be greater or equal to 4, it's always going to guarantee that k plus 1 is going to be greater than 2. Okay, so instead of putting 20,000 there, let's put in k plus 1. K plus 1 is greater than 2, which now is what I mean. You can see the kind of the niceness of this step here, that tells you that k plus 1 times k factorial. K plus 1 times k factorial is nothing but k plus 1 factorial. So this entire statement in blue here, everything in blue here now can be written as 2 to the power of k plus 1 is less than k plus 1 factorial. Okay, so and this is how you can show that the inductive hypothesis is also true for all k.